This presentation is about the idea of a t-distribution. This is a conceptual explanation, skipping over a lot of the mathematical nitty-gritty, because once you've understood the concept, it's easier to fill in the math. And vice versa, some of you may already know how to compute using the t-distribution for confidence interval or hypothesis testing of a mean. And you want to know why we use a t-distribution, and this presentation fills in the blank. It starts with the idea that statistical inference is based on the central limit theorem and sampling distribution. The CLT for proportions, for example, says that under certain conditions, the sampling distribution for the proportion is normal or approximately normal with the mean equal to P and standard error equal to square root of P times 1 minus P over N. And we use that for inference. For example, a 95% confidence interval on a proportion. If we compute a 95% confidence interval of a proportion, we get it from this normal distribution with 95% confidence level in the middle. The mean and standard error of distribution are based on P, which we can approximate by using p hat. And when we standardize using the z-score formula, x minus the mean, which is p, divided by standard error, which is a formula involving p, or rather p hat if we substitute p hat in it, then we get the z distribution, standard normal z distribution with a mean of 0, and the critical value z star at the end of the 95% area. And now for the mean. The CLT for mean says that under certain conditions, the sampling distribution for the mean is normal or approximately normal with mean of mu and standard error of sigma over square root of n. So we can use that for inference on the mean just like we did for proportion. So let's say we compute a 95% confidence interval. Because of the central limit theorem, we can use the normal distribution. This normal distribution has a mean of mu and standard error of sigma over square root of n, which we then can standardize using the z-score formula, and we get the standard normal distribution z with a mean of 0, 95% confidence level area in the middle, and the critical value z star just like before. But if you look at the z-score formula, you will see that we need the mean, which is equal to mu, and we need the standard error, which is equal to sigma over square root of n. Mu we don't know, but we're going to substitute x bar just like for proportion. P we don't know, but we're going to substitute p hat, the sample proportion. That goes in this part of the z-score formula. And then we need the standard error into that part of the z-score formula. And this is what happens. What happens is we probably don't know sigma either. You think about it, we almost never know sigma. We have a population where we don't know what the mean is. So that's why we're doing a confidence interval for mu in the first place. Well, if we don't know the mean, we're not going to know the standard deviation. We almost never know the true value of this population standard deviation, sigma. So fine, we do it like we always do. If we don't know the population parameter, we're going to substitute the sample statistic. We don't know sigma, we will substitute S. And that's okay, but except this, you've introduced more error than the central limit theorem expects. If we knew sigma, we would have this distribution of z, the standard normal distribution with a mean of 0, and a 95% confidence level in the middle. But we don't know sigma, and we're substituting S. That means we're introducing more error into this diagram. And more error means less confidence. That means this 0.95 confidence level in the middle cannot be 0.95. Whatever it is, it'll be less than 0.95. So the area cannot be 0.95, you have to be less. That means you'll be a smaller area in the middle. And because the area of the whole graph has to be 1, when you have less area in the middle, you have more area on the outside. What we need is a distribution where it looks like the Z distribution, except that it's shorter in the middle and thicker on the tails. This new distribution is called the T distribution. The T distribution is like the Z distribution with a mean of 0, except it's shorter in the middle and thicker at the tails. And it reflects that we have more error introduced into the calculations by substituting S for sigma. Which brings us to the next thought. How much error is in an approximation depends on how big your sample is. In general, small samples not as good as large samples. When you have a small sample, you have a lot of error, then your T curve will be very different from the standard normal Z. But when you have a larger sample, then you have less error and your T curve is not that different from the Z curve. So that tells us that there's not just a single T distribution out there, but there are many T distributions depending on how large a sample is. And that brings us to the concept of degrees of freedom. The degrees of freedom of a T curve is defined as n-1, where n is the sample size. When you have a small sample, let's say of size 10, then it has 9 degrees of freedom. And a T curve with 9 degrees of freedom is very different from the Z curve. When you have a larger sample, let's say sample size 25, then it has 24 degrees of freedom, and the T curve is closer to the Z curve. And when you have a very large sample, let's say size 50, 60, 70, then they are very, very close to the Z curve. So we say that the T distributions approach the Z distribution as the sample size gets large. So in summary, here are the ideas involving the T distribution. We use a T distribution to do inference, meaning confidence interval and hypothesis testing on the mean when sigma is unknown. Be careful that the sample standard deviation is always known. So when the problem says the standard deviation is equal to something, read it carefully to see if it's sigma or if it's S. If it's S, then that means sigma is unknown and we use the T distribution. There are actually many T distributions, each of them looking like Z with the mean of 0, but shorter in the middle and thicker in the tails. The mean of a T distribution is 0, and each T distribution comes with its degrees of freedom. df is equal to n-1. And as the sample size gets large, as the degrees of freedom get large, the T distribution becomes more similar to the standard normal Z distribution. All right, so that's the idea of the T distribution. Thanks for watching. Bye.